So hello everyone, myself Anand, and today I am going to explain the concept of aromaticity of annulene rings. So before I start, let me explain what are annulene rings. So annulene rings are when a compound have a conjugative pi bond, then we can call it an annulene if it have planarity too. Like if I take a simple example like a benzene ring, then what we had in that is ki this ring is small in size, that's why it lies in single plane. Okay, and it have conjugated pi bonds, and the electrons of these pi bonds can circulate in a single plane, which makes that benzene ring more stable towards reaction, and also make this compound more aromatic. I hope I have made myself clear. Let me move to the next compound, that is 10 annulenes. Wait, that is 10 annulenes. 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this particular compound have 10 number of carbons, so we will represent them in such brackets, and then write simple annulenes. This is the name of this compound. Okay, so it also have alternate sigma and pi bond, and these pi electrons can circulate in the whole ring. But the problem here is that the planarity of that compound, the compound is such a huge that it cannot lie in the single plane. So what it does, it just get bent and redefine its shape in such a way that it forms a semi benzene ring, but still they are not aromatic. The reason behind is that they have two hydrogen atoms here. Let me zoom this compound. That there are two hydrogen between that bridge. This is a bridge head carbon, and this is a bridge head carbon. It is not yet bridge head, but it will be bridge head later. Okay, so because of these H atoms repulsion, this compound turns into a open book structure type, like it bends like this. Okay, yeah, so this is the exact shape how it redefine its structure. But what if we place uh, we place any small atom on its joints? Like if we remove these hydrogens and place a small element over there, so it will, if we place this x atom on its bridge head position, then this carbon will push this angle lower side, and this will turn into a planar structure. And the moment it become planar, it will become aromatic, because it have all the properties which a aromatic compound should have, except the planarity. But the moment this compound arises on its bridgehead position, this structure turns into a planarity, and that whole compound become planar. Okay, and one more thing, like we cannot place a very big and heavy atom on x position. So x, what can be x can be a small compound like oxygen, uh, fluorine, chlorine, uh, nitrogen. So they must be a small in size, because if we place a heavy compound on x position, then this ring, then this planarity will turn and flip into the other side, and form itself in such a structure. So again, heavy atom will be not beneficial for us. Okay, I try to keep myself into the frame so that I think I had made myself clear. Okay, let me move to the next compound. That is let me name number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So its name is 12 annulenes. 12 annulenes. Okay, and it have a proper circulation of electrons. Yes. So, and here are the hydrogen atoms. Okay, so as we seen in the as we saw in this compound that this compound was not aromatic till we don't place any atom on its bridge head position because of the H repulsions. So we have the same problem in this compound because of the repulsion of these small tiny uh, hydrogen atoms. They don't make, they try to repel each other from the each they try to repel each other from uh, okay, retake. So this compound is not aromatic because of the hydrogen repulsions. Here are four hydrogen atoms and they repel each other, which makes that compound non-planar. But what if we increase the number of carbon in this ring and provide extra space for these hydrogen atoms, then it will lead to decrease the repulsion between the hydrogen atoms, and this compound may come in a single plane, and the moment it come in the single plane, it will be a aromatic compound. Let me present next example. But for a moment this compound is non-aromatic. Okay, non-aromatic. It's 12 annuline. Wow, we have the next compound that is it's 18 annulene. It's 18 annulene. Okay, and it also have the same uh, configuration like we have hydrogen atoms here, but like you can see right here we have less amount of space at the center, and here we have a large amount of space at the center. So because we have large cavity here, so there is a less repulsion between the hydrogen atoms, and if they have less repulsion, then they will be stable, and this molecule will lie in a single plane, and the moment it lies in the single plane, it will become a aromatic compound. The main problem is the repulsion between the hydrogen atoms. Here repulsions are more, which make them non-aromatic, and here repulsions are less because of the large ring. So this compound is an aromatic compound. Okay, and the next compound is this. Obviously it is not aniline ring, but we can see here a periplanar, a perimetric resonance. So let me explain that because if like advance, I think advance had asked one time about that compound, like how many pi bonds are taking part in that resonance. So if we look at the first side, like 1, 2, 3, 4, 5, 6, 7, 8, 8 pi bonds are taking part in the resonance in first look, but that's not the correct picture, because if we look at the diagram, what it says, this pi bond move here, it moves here, it moves here, and it moves here, it moves here, it moves here, it moves here, it moves here. So this pi bond is not taking part in the parametric resonance, and if this pi bond takes part in the aromatic resonance, then the aromaticity of the compound decreases. So because of that reason, this pi electron does not take part in the aromatic ring. So if we remove that pi bond, the compound will be still a aromatic compound. So next time if someone asks, just say it have 1, 2, 3, 4, 5, 6, 7. Only 7 pi bonds or pi electrons are taking part in the resonance. This bond is, or this pi electron is not taking part in the resonance. Okay, let me explain a very classical example of perimetric resonance and the cavity repulsion. So this compound is a thiophene, and this compound is thiophene, and this is a furan, annulene. Okay. So what it is like 1 2 3 4, 1 2 3. Okay. So what now we can see that it have a lone pair here. Okay. So these lone pairs are taking part in a ring if we isolate this, but if we connect them in consecutively, then they form a big large ring. And this compound is stable till there is a rest repulsion in the cavity region, and the moment cavity size decreases, then repulsion increases. So as we all know that oxygen atoms are smaller than sulfur atom, so cavity then less amount of cavity required, and repulsion will be less in the oxygen atom. But if we take the same example in the sulfur atom, then sulfur atoms are size are bigger than the oxygen atom, so they will repel each other, and the repulsion causes non-planarity. And as we all know that sulfur thiophene have a good amount of aromaticity because of lone pair. This compound, this particular unit is aromatic, but that compound is not aromatic, but this unit is individually not aromatic. Why? Because it turned itself into this kind of a structure, because of the small size of cavity and big size of sulfur atom. So they repel from that cavity and flip themselves in such a way that repulsion decreases, and because of that flipping, aromaticity of that thiophene decreases. And as we all know that this compound aromatic in all states, this unit is aromatic also, and this individually is also aromatic. So we can say that oxygenated compound is aromatic, and this is not aromatic. So I think I had made myself clear. Thank you.